So here are the two primary objectives of our inverter. Our inverter should produce an AC voltage VAC across terminals A and B for a fixed DC with a given fixed DC voltage, and the fundamental component of the output voltage VAC1, it should be controllable, because we are able to turn on and off the switches, right? So by turning on and off the switches appropriately, we should be able to control the fundamental component of this AC voltage VAC1. And when we say we want to control, what do we mean? We want to control its magnitude and also frequency, because it's not necessary that we just always want to generate 50 Hz, because the source that is present within this load, the AC source that is present within this load, the back EMF source that was shown earlier, it could be at any frequency. It depends on the speed basically. It could be at 20 Hz, it could be at 15 Hz, depending on the speed at which a motor is rotating, for example. So it is not necessary, it's not always necessary that the voltage across A and B, which is the VAC, has only 50 Hz fundamental component. It could have 15 Hz fundamental component, or it could have 20 Hz fundamental component also. But whatever the fundamental component may be required as per the operating condition, we should be able to generate, the inverter should be able to generate that particular voltage at having that fundamental component. And what is the other objective? Whatever the remaining component is, at whatever frequency the remaining components are, we want to minimize them as much as possible, because they are not causing net energy transfer. And why? Because we have a pure sinusoidal voltage that is sitting inside most of the loads. With the objectives of inverter defined, a voltage source inverter, because this is a voltage source inverter, we are trying to create a voltage which is defined, but the current drawn is depending upon the load. That is why the type of inverters that we are discussing are known as voltage source inverters. Voltage source inverters, VSI. Because we are not defining the current that will be drawn from this inverter, that will be defined by the load. There are also current source inverters, but voltage source inverters are more popular, and that is why we are discussing them in this course. Now, having defined the objectives of our voltage source inverters, let us try to look at what we have learnt. Let us try to relate those objectives to what we have learnt. We have learned that we can produce a square wave AC voltage, and if you consider this green color square wave AC voltage that is drawn, and how are we producing it? By again turning the diagonal switches on and off for equal intervals. The fundamental component of the square wave is 4 VDC by pi, as we know, the peak value of the fundamental component, and any nth harmonic component can be, or the magnitude of any nth harmonic component is 4 VDC by n pi. So for a fixed VDC, for a given VDC, magnitude of the fundamental component is fixed. If you are doing this square wave kind of switching, or if you are turning the switches on and off to generate a square wave, your magnitude of fundamental component is not controllable, because usually we have this very stiff DC voltage input. But how about the frequency of the fundamental component? Yes, it is controllable. It can be varied. How? It can be varied by varying the intervals for which these voltages are applied. And how about the harmonics? Harmonics, all of them, all odd order harmonics are present. Third harmonic, fifth harmonic, seventh harmonic, and so on, which are not desirable. So we need to look at a better method. Let us say we have turned on the switches S1 and S2 and S3, S4 appropriately such that we can generate this particular voltage with having not just VDC and minus VDC, we also switch in such a way that the voltage is 0 in some intervals. And how do we make sure that the voltage is 0? By simply turning on S1, S3 together, or by simply turning on S2, S4 together. It is like a short circuiting the load, but it's only for a small interval, so it's acceptable. So we have generated this kind of voltage, the second kind of voltage that is shown, and we have to have this alpha angle symmetrically placed because we don't want to generate even harmonics, so we need to maintain half-wave symmetry. What happens to the fundamental component now? VAC1 is now a function of alpha, of course for a given VDC. VDC is always fixed, and VACN also is a function of alpha, By varying alpha appropriately, we can control the magnitude of VAC1. That is one objective. Or by varying alpha appropriately, we can make sure that some harmonics are not present, which is the second objective. But if you want to do both, we need to find a solution. Okay, we specify one particular fundamental. I want this much magnitude fundamental voltage, and I don't want harmonic of this particular frequency, or I want harmonic of this much magnitude. So we should be able to find a solution mathematically for this value of alpha and appropriately generate the voltage or generate the switching pattern which will generate the voltage. Let us go one step further. We introduce more instants which are defined by the user. Instants of switching, turning on, turning off. For example, alpha 1, alpha 2, alpha 3 in this kind of waveform, third waveform. And of course, we have to place the switching instance in such a way that we maintain half-wave symmetry and also quarter-wave symmetry if desirable. Now what will happen? Any nth harmonic component, including the fundamental component, will be a function of alpha 1, alpha 2, alpha 3 for a given DC voltage. So we can find a solution for alpha 1, alpha 2, alpha 3 to achieve the desired objective. So much given fundamental voltage and so much third harmonic, or 0 fifth harmonic or 0 seventh harmonic, and so on. Basically, we will be solving a system of nonlinear equations and arriving at the instants alpha 1, alpha 2, alpha 3 and switching the switches appropriately. What are we doing here? If you observe, we are creating pulses. Because we have fixed DC voltage and the pulses are varying between 0 and VDC or minus VDC and VDC. So the pulses are being created, and these pulses, the width of these pulses is also being changed or modulated in certain fashion. You have a small pulse, then you have a larger pulse, then you have a wider pulse, and then the wider pulse becomes smaller because symmetry has to be maintained. So we have certain train of pulses that are being generated whose width is being modulated. And why is it done? It is done to achieve the desired objective. And what are the desired objectives? Controlling the magnitude and frequency of the fundamental component and minimizing the harmonics. So in order to achieve these objectives, we are modulating the pulses. We are generating pulses by turning on and off the switches, and we are also modulating their widths. So this is known as pulse width modulation, and it is required to achieve the objectives of any inverter. And this particular way of doing PWM or pulse width modulation, by calculating the switching instants alpha 1, alpha 2, alpha 3 ahead, like even before we start to build some circuit or we start to implement this way of switching, we need to know what this alpha 1, alpha 2, alpha 3 are. right? One needs to solve this system of nonlinear equations to meet the required specifications and come up with the instance of switching alpha 1, alpha 2, alpha 3, and once he comes up with those instance of switching, and he can turn on or off the switches appropriately. So this kind of switching angle calculation ahead of implementation is known as offline PWM. It is offline PWM because the switching instants are calculated offline, and this method of offline calculation of switching angles is popularly used to eliminate the unwanted harmonics, certain unwanted components. It is used to eliminate because we can use it for multiple purposes. This alpha 1, alpha 2, alpha 3 or alpha n in the generic case can be used to generate a required fundamental component, and in addition to that we can also use them to mitigate unwanted harmonics. So mitigating unwanted harmonics becomes more prominent because we will be doing many things. That is why this is popularly known as selective harmonic elimination pulse width modulation, SHE PWM.